Hi, this is Mr. Doro. Today we're going to be talking about the ideal gas law. The ideal gas law is written out in the equation PV equals nRT. Most of these are things that we've dealt with before in the other gas laws. We haven't really dealt with the number of moles N, and we definitely have not dealt with the gas constant R. Now, the thing you got to realize about the gas constant is that it is a constant. That means it does not change. It will be the same every time. It may have different units, which makes the number look a little bit different, and you have to choose which one you're going to use, but it is a constant. You have to remember that. With the ideal gas law, it puts together all the gas laws that we've learned to make up this ideal gas law, PV equals nRT. And we already talked about R being the universal gas constant. We're going to see what those values are next. But something you got to know about it is it does not work well at low temperatures and high pressures. And that's because ideal gas laws, they assume that they're going to act in certain ways. But at low temperatures, they slow right down. Those molecules slow right down and they come back closer together, act more like a liquid or a solid, and so they don't follow the ideal gas law. Same thing with high pressures. High pressures, they're being forced close together, and as they do that, they're acting less and less like a gas. Here are those values for R, the universal gas constant, that you're going to want to write down. These units are a little bit weird on here. This first one is 0.08206. The units are all four of these together: liter, atmospheres, per mole Kelvin. And you have to write those units each time, and it's just weird, but that's what you have to do. 8.314, these are both 8.314. The one that you're going to use most often is this one, liter kilopascals per mole Kelvin. And then 62.4 liter millimeters of mercury per mole Kelvin. And as you can see, these are all liters, moles, Kelvin. The only thing that really is different in here is the units for the pressure. This one is for atmospheres, this one's for kilopascals, this one's for millimeters of mercury. And joules is a pascal per meter cube, but we don't have to know that for right now. You just got to know these three, have them written down for your values of R. Since we haven't talked about the number of moles much at all, I wanted to introduce you to a couple things about how the number of moles stays constant. Once you get the number of moles, unless you add gas to it or take gas away from it, then the number of moles are going to stay constant. These three pictures show three different cubes with a mole of gas inside the balloons. So inside this balloon, there's 1 mole of gas. Inside this balloon, there's 1 mole of gas. And inside this one, there's 1 mole of gas. But if you look at the surrounding temperature and pressure, this is at medium temperature and medium pressure. And you can see that it's not pushing in all that much. It looks like a normal sized balloon. But if we increase the temperature inside of here and we have a very low pressure, then this is going to expand outside a little bit further. The balloon's going to get bigger. And if we have a low temperature and a high pressure, more molecules in here pushing in on it, it's going to push more and more. That brings us to a point that we haven't talked about, and that is called standard molar volume. And you want to write this down. Standard molar volume. And what that means is that 1 mole of gas at STP, standard temperature and pressure, would be 22.4 liters. That's how much volume it would occupy. That is called the standard molar volume. That's only at STP though, and sometimes we have a lot of different temperatures and pressures, so we have to use the ideal gas law to figure those out. So here's a typical ideal gas law problem. It says, what volume would 2.84 moles of an ideal gas occupy at 1.96 atmospheres and 323 K? So we got to label what we've got here. This is obviously number of moles, N, because it says moles right there. This atmospheres is going to be my pressure. This is my temperature right here. And so now what I have to do is use my ideal gas law, PV equals nRT. In this case, we're solving for the volume right here, and so we could change it around to get V all by itself, but I'd just rather plug in the numbers and get it all taken care of here. So my pressure is 1.96 atm. My volume is what I'm solving for. My number of moles is 2.84 moles, and it doesn't even say what gas it is. It's just 2.84 moles of that ideal gas. My R, this is where I have to pick my R value, and so I'm going to pick the one that has atmospheres with it. And so if I look back at my notes and I find out which one has atmospheres in it, it is 0.08206 liter atmospheres per mole Kelvin. Yes, you have to write it out, and there's a reason why. And then my temperature, T, is 323 K. And so if you look at this, my Kelvin temperatures are going to end up canceling out right here. My moles are going to cancel out. My atmospheres, when I bring that 1.996 atmospheres over, they're going to end up canceling out, and I'm going to be left over with liters, which is my unit for volume. So this is going to be V equals, in order to solve this, I'm going to do 2.84 times 0.08206 times 323, and then to get this over on the other side, I'm dividing both sides by it, so I'm dividing by 1.96. And my sig figs should be 3 sig figs, because that's the least number I have there. I got 38.4057, blah, 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 blah. And so I'm going to call that 38.4, and that is liters. And that's my answer right there. Sometimes you might be wondering, when do you use the ideal gas law? And if you look at this, we are given moles, but we're only given one pressure, one temperature, and that's all we're given. We're not given two pressures or two temperatures, and then we could use a different law that we have used in the past. But when we're only given one of each of these, remember we got that ideal gas law or universal gas constant that we can use and plug in there for the ideal gas law. Okay, here's another problem. This one's a little bit different. It's asking for how many grams of oxygen gas would be present at 99.8 kPa. That's my pressure, because that's a unit for pressure. 20.0 liters, that's my volume, in standard temperature, which tells me that my temperature is going to be 273 K. And so I'm going to plug this in and to my ideal gas law, which is PV equals nRT. And my pressure is 99.8 kPa. My volume is 20.0 liters. And N, I don't know what N is. It wants me to find grams, which is not N, but I can get grams from moles. And then my R is going to be in the kPa, which is going to be 8.314 liter kilopascals per mole Kelvin, and my temperature is going to be 273 K. Alright, so then I look and see what cancels out here. My kelvins are going to cancel out. I have kPAs on this side and kPAs over here on this side. I have liters over here, liters over here. My answer when I solve for it should end up being in moles. Now I know moles is on the bottom, but I'm going to switch everything over so that I get this N all by itself. The way I'm going to do that is I'm going to divide both sides over here by 8.314 and 273. So really these come over and go down here on the bottom. I get 99.8 times 20.0 divided by 8.314 and then divided by 273. So I'm going to plug those in right now. And I got N to equal, because that's what I'm solving for, 0.879. Now my units on that are moles. And this is moles of oxygen gas, so that's O2. But the question, remember, says how many grams of oxygen gas are there. Now you guys know how to do this. You can change that moles to grams by doing a simple one-step action line. And that looks like this. You start out with 0.879 moles of O2. And then moles of O2 have to go on the bottom. And then we go to grams of O2. Remember, every time you got grams and moles, we put a 1 for the moles. This is off the periodic table. O2, oxygen, is 16.00 times 2, which makes 32.00. And then you plug that in. And you get 28.1 grams of oxygen. So you can go to grams by using the ideal gas law, but you have to go to moles first. So here are two problems for you to try. The first one is pretty much a straight up ideal gas law problem. Gives you moles and atmospheres and liters and asks you to find temperature. And then the second one gets a little bit trickier. So as you look at the second one, notice it gives you grams of carbon dioxide. And there are no grams in the ideal gas law, but there's something in the ideal gas law that you can change grams to in order to help you out. It also gives you this 398K, and it gives you this standard pressure, so don't forget about that. That's something that should be able to help you out also. As to find volume, make sure you're showing your units. Make sure when you're doing this, you're writing the formula each time. You're plugging them in the correct area with the units on there too. So go ahead and get these done. They won't take all that long, and hopefully we'll check them tomorrow. Bye-bye. Have a good night.